Okay, so now we want to take the results from the last couple of movies and put them together and try to see if we can derive a picture of the phase diagram. So let's recall the problem. So we have these two differential equations, dx dt is equal to x minus y, dy dt equals x squared minus 4. We have computed the null clines. The null clines are what happens when you set the right-hand side of each of the two equations equal to 0. So for the first equation, we got x equals y, and for the second equation, we got x equals plus or minus 2. And then we also derive the fixed points, which are the points where both dx dt and dy dt are the 0. Those are actually the intersections of the null cline. And we found that the one at 2, 2 is an unstable spiral, whereas the one at minus 2 is a saddle with the rough characteristics that are shown here. So now what I'd like to do is try to put this all together and sketch the phase. Okay, so now the goal is to draw the phase diagram. So as you know, I can't draw, and so this is very challenging for me. But I will just draw x and y axes here and here. And then let's start out by drawing the null clines. And just for fun, I think I'll make them blue. So here is x equals 1, here's x equals 2, here's x equals minus 1, minus 2. So we have one vertical line at x equals 2. We have another vertical line at x equals minus 2. So that's x equals 2 null cline. This is x equals minus 2. And then we have another null cline, which is at y equals x. You will note, and we might as well just put on here, that the fixed points are the intersections of the null cline. There's one fixed point in purple, and there's the other. And now let's draw the velocity arrows that are implied by the null clines. So what we know is that when x is equal to 2, if y is bigger than x, then there's only an x component to the velocity, and it is pointing in the negative direction. That's basically what the equations say. Whereas if y is less than x, then it is pointing in the positive direction. So that's that. And we can apply that here too. Negative direction if y is bigger than x. Positive direction if y is less than x. Okay, and then the other null cline at y equals x has the feature that the velocity vectors are in the positive direction. And what we know is that if y is equal to x, and if x squared is bigger than 4, then this is positive. Whereas if x squared is less than 4, then it is negative, which is here. And then when x is more negative than minus 2, x squared is again bigger than 4. So we go back to positive. Okay, and so that's that. So now what we want to do is to draw the flow lines of this. And you will recall from our stability analysis that we decided that the point at the fixed point here at 2, 2 was an unstable spiral. And indeed, we see that the flow lines are spiraling around it. So that's consistent. So let me just draw sort of a spiral because these things are spiraling around. I'll just draw some arrows. So that's basically what we expect. We expect it here to go like that. So I'm just going to try to connect the dots. So you see this becomes art at some point. We're just trying to connect the dots to each other. And but then when you look down at the fixed point over here at minus 2, you see there's a bit of a contradiction. The arrows are actually contradicting each other. And that contradiction actually is resolved if you just remember for yourself the unstable directions. And that's sort of something like this was the stable direction, and this, something like this, was the unstable direction. So if I just sort of go with that, that's unstable, and that's stable, then actually everything sort of starts to make sense. So basically we're getting this in here, and then over here we must have a flow which basically goes like this. So you see I'm just sort of by eye connecting the arrows. All of these things have to end up pointing along these directions. Here, this direction is also stable, so these things are going like this, and that's sort of what it has to be. And so basically this gives us a rough picture of how everything fits together just from pure sketching. And now what I want to do is show you the answer so we can see how well we've done. So this is our crazy little sketch, which we got by combining sort of several things, remember? So we combined the null clines, we combined the fixed points, and we just drew velocity arrows as best as we could. So let me now show you the answer. Okay, here we come. So this is the answer. So this is a phased plane that I computed using MATLAB, and we can just try to sort of look at it and see how well we did. So you'll see the fixed points are here and here. I can just start by drawing the axes. So let's see. Maybe I'll draw the null lines actually. So here's x equals 2. Here's x equals minus 2. And let's see if we can do this. The line y equals x should be basically right here. Y equals x. So you see actually if you look at the flow, then just as we said, the velocity vectors are pointing in the directions that we guessed. They're pointing this way along below the thing and this way above the thing. We along this line they're pointing vertical here. They're pointing vertical there. They're pointing up here this way and this way. You see the unstable spirals that we talked about. You see, let's see, and you also see what is evident is the unstable manifold and the stable manifold of this fixed point. I mean, if I were to draw it, roughly there's one there, and there's one sort of, let's see if I can draw this roughly. So here the flows are going away, and then here's the sort of stable manifold where they're basically coming in, and the flow arrows have connected together in much the way that we described. So in any case, this is a way of sort of thinking your way through a phase portrait. When I do this, I like to understand qualitatively how it works, and so I start with the null lines and fixed points and stable manifolds and spirals and things like that, and then it's useful to make a plot and just see how well you did.